So today we're going to be looking at the kinetic energy of gases. And of course, kinetic energy, we remember, is the energy of objects that are in motion. And so that imparts to us the idea that gases have kinetic energy because they are in motion. And we know that this is the case because of something that we've heard before called kinetic molecular theory, which says that all molecules are always in motion. We're going to put a little asterisk next to this always because we know that there's always an exception to every rule, especially in chemistry, but for the most part, this holds true. And here we have a nice little simulation that shows us exactly what's going on. Here is our chamber. Currently our pressure is 0 atmospheres. And I'm going to pump this handle and inject some gas particles into this chamber. And you can see that as they start hitting the sides of the vessel, that our pressure goes up. When we're at 300 kelvins, about 27 degrees Celsius. Well, what happens to this pressure, and what's causing it? Obviously, the particles themselves hitting the sides of the container are, what is causing pressure. And if we were to make this vessel bigger, all of a sudden our pressure drops because we're not impacting the sides of the vessel as often as we were. So what we're going to do is we're going to try to increase the pressure by another way, and that's by increasing the temperature. So you can see that the temperature is increasing. We're at 500 kelvins, and look at the gauge on our pressure. It's increasing dramatically because the speed with which our gas particles are moving is also dramatically increasing. They're not only hitting each other harder, but they're hitting the sides of the vessel harder, and that's making our pressure increase. So we know that the kinetic energy of particles of any gas have a lot to do with the temperature. Well, we remember that from our old friend, the ideal gas law, which says that PV equals nRT. And if we flip this around a little bit, P is equal to nRT over V. And what this means is that if we were to increase the temperature, our pressure would increase. If we were to increase the number of moles of gas, our pressure would increase. If we were to increase the volume, making the volume bigger, our pressure would decrease. So what is causing these gases to actually exert pressure? Well, they're in motion, and that means that they have kinetic energy. So in physics, kinetic energy is measured by an equation that looks like this. Kinetic energy is equal to 1/2 mv squared, where this Ke is our kinetic energy in joules. And we'll abbreviate that J. This is, of course, our mass in kilograms, and this final variable is our velocity in meters per second. And let's be careful here because it is being squared here, and that means that there is another way to write these units, that a joule is the equivalent of a kilogram times a meter per second squared, or in other words, a joule is equal to a kilogram times a meter squared over a kilogram squared. Well, how does this relate to temperature? Obviously, temperature has a lot to do with velocity. And so if we were to take out this proportionality in our equation, if we were to say that PV equals nRT, and if we were to say that this R, our gas constant, if we were to get rid of that for just a second, that would make these proportions. PV is proportional to T. And that means that P is proportional to NT over V, meaning that the pressure increases as our number of moles increases, as our temperature increases, and as our volume decreases. So what we're going to do is we're going to, since this is a relationship of temperature, we'll rearrange this equation to find temperature. And so if we were to take all this stuff out, if PV is proportional to NT, that means that T is proportional to PV over N. Well, if we were to plug all of these variables back in, including our constant, which is a proportionality constant, that means that PV over N is equal to RT. And that constant throws a little monkey wrench into our equation, but we'll simply say this. If this is proportional to RT, then kinetic energy is also proportional, and if we throw in our constant, that makes our temperature equal to 2/3 of our kinetic energy. And this is going to be our average kinetic energy for our entire sample. Well, if we don't want to mess with any of this pressure and volume stuff, we can simply say this. If RT is equal to 2/3 the average kinetic energy, then our kinetic energy of our average molecule is going to be equal to 3/2 RT. But let's be careful, because when we were using our old buddy PivNert, the value for our constant R was 0.0821 liter atmospheres over moles kelvins. Well, that's not going to work here because we are referring this to the unit for kinetic energy, and that involves joules. So we're going to use a different value for R. And for this case, R is going to be equal to 8.314 joules over moles Kelvin. So be careful, because the value for R is different depending on context. All right, let's try one of these. So we're going to ask, what is the average kinetic energy, for a sample of O2 at 25 degrees Celsius, if we know that the equation for average kinetic energy is equal to 3/2 RT, where R is equal to 8.314 joules over moles Kelvin. Well, we're going to get our temperature into kelvins, because obviously it's not going to work on this, if we still are in degrees Celsius. So let's plug everything in. Our average kinetic energy is going to be equal to 3/2. This is our value for R, 8.314 joules over moles Kelvin, times our temperature, 298 kelvins, right? We're just going to add 273 to our temperature, and look what happens to our units. Kelvins cancel. It gives us our answer in not just joules, but in joules per mole. So let's bust out our calculator. So we'll say 3/2, obviously that's 1.5, times 8.314, 8.314 times 298. And here is our answer in joules per mole, 3,716.4, we'll call that. So 3,716.4 joules per mole. So if kinetic energy is a measure, a calculation using the equation 1/2 mv squared, that means we should be able to calculate the velocity of a molecule in meters per second. We're going to write this a little differently. The equation in your textbook doesn't use a v. It uses a u. So we're going to use that just so that we are consistent. And they call this the root mean square velocity. And what this means, root mean square, it just means it's the average velocity in meters per second for the molecules in a sample. Because if we look at this particular sample, I mean, it's pretty obvious that different molecules are moving at different speeds. So this is going to calculate what we're going to call the root mean square velocity. It just means the average velocity of particles in a gas at a given temperature. And so it's going to work like this. If we know that the average kinetic energy of a bunch of molecules, average, is equal to 3/2 RT, but we also know that kinetic energy, average, is equal to 1/2 m, and we're going to use a u, not a v this time, then what we have is this. 1/2 m u squared equals 3/2 RT. Well, what do you get if you try to isolate u and solve for the velocity? So we get this. We get u squared equals 3/2 RT over 1/2 m. And of course, the halves cancel. So now what we have is 3 RT over m. And since we're trying to find not the square of the velocity, but the velocity itself, let's make this look like this. We'll get rid of the square by square rooting everything, and so now we have velocity equals the square root of 3 RT over m. But we got to be careful. This must be in kilograms. So to remind myself that it needs to be in kilograms, I'm going to use a capital M. So there's our equation for what we call the root mean square velocity. Let's try one. So what is going to be the root mean square velocity for a sample of oxygen gas at 25 degrees Celsius? And we already know that the root mean square velocity is equal to the square root of 3 RT over m, where T is the temperature, M is the mass in kilograms. Let's make sure we keep that in straight in kilograms. And R is our old buddy, the gas constant. So let's plug some stuff in and see what we get. We are talking about a sample of oxygen gas at 25 degrees Celsius. And oxygen, let's remember, has a molar mass of 16 grams. That means for O2 it's going to be 32, and so our mass in kilograms will simply be 32 divided by 1,000. Let's plug it in and see what we get. So we're going to take the square root. We're going to say 3. The value of R is 8.314 joules over moles Kelvin times our temperature. 25 degrees Celsius is 298 kelvins. And our mass is 32 grams, but in kilograms, 0.032 kilograms. Now this might look like a mess, but let's start canceling units out and see what happens. Obviously, kelvins is going to cancel. And if we recall from way up here at the top, way up here, another way of saying a joule is a kilogram times a meter squared over second squared. That should say seconds. Oops, that should say seconds squared. So let's take that and plug that into wherever we see a joule. Let's get rid of this, and we'll replace that with a kilogram times a meter squared over second squared. And now kilograms cancel. That leaves our unit in meters squared over second squared, and we're going to take the square root of that. And so, let's bust out our calculator. Our answer is going to be in meters per second because we're taking the square root of meters squared per second squared. Here's my calculator. So let's crank this out. So here's 3 times 8.314 times 298. We're going to divide this by 0.032. And then we'll simply take the square root of this, and this will be our answer. 482 meters per second.